Hello, I'm Wonjun Moon from Sungkyunkwan University to introduce the paper Tailoring Self-Supervision for Supervised Learning. Recently, along with the success of self-supervised learning in the unsupervised domain, many papers have introduced adopting self-supervision into supervised domain because it actually helps in some aspects. Rotation and jigsaw and etc. are the popular techniques. Still, as these methods are devised for the unsupervised domain, without the objective of self-supervision should be modified to be tailored for supervised learning. Thus, we first suggest three desired properties of self-supervision for supervised learning. First, self-supervision should guide a model to extract rich representation. Previously, the aim of self-supervision was to learn general features. However, in the supervised domain, we already have supervised objective function. Therefore, we thought self-supervision could be more helpful if the objective is to complement supervised objective. For example, shortcut learning is a problematic issue in the supervised domain that the model tends to only focus on the most discriminative parts in the image. By handling these kind of issues, self-supervision can guide a model to learn richer features. Second, transformations for self-supervision should not significantly modify the image. Indeed, some papers have indicated that some pretext tasks or transformations might degrade the performance when used as augmentation or in the form of multitask learning. Therefore, previous works employ self-supervision in the sacrifice of the applicability. However, in the perspective of improving supervised learning, applicability is another essential point of self-supervision. In fact, the form of pure task learning that the previous works use takes at least twice the training cost. To satisfy the mentioned desired properties, we propose localizable rotation, LOROT. Simply put, LOROT samples the patch and rotates the patch. In this work, we introduced two variants of LOROT named LOROT I and LOROT E. The difference between the two is that while both produce the keys to predict the rotation degree, LOROT E explicitly asks the model to also predict the position of the patch. Now, I'll explain how LoRa satisfies the properties. First, let's assume that the model conceives the big and the fatter as the most discriminative parts of the bird. Generally, when the model discovers the most discriminative parts of the object, it often does not guess to learn more about the object. However, assume that the LoRa rotated the patch corresponding to the feet. Then, to solve the LoRa, the model gets to focus on the feet. This way, LoRa can guide the model to learn more features about the object. Here's our visualization. Compared to the baselines, we observe that the model trained with LoRa focuses more thoroughly on the object. The second property was that the transformation should not incur much distribution shift. However, as LoRa only selects a patch to rotate, the distribution shift is much alleviated. To support the claim, with the affinity measure, we can see that the data distribution is much more preserved than rotation. Visualization also shows the same result. Lastly, we believe that the LoRa has high applicability. This is because LoRa is implemented in the form of multitask learning. Not only the method is simple to implement, but for the standard ImageNet classification task, there is only a 0.1% increase in parameters and 6% in the training time. Thus, compared to previous works that cost at least twice the original training time, the computation cost is much reduced. Here is our experiment. The table on the left is about how well the model detects out of distribution samples, and the table on the right shows the performance for imbalance classification. For more results on the various benchmarks, including classification and robustness and so on, and also the compatibility with contrast learning and augmentation techniques, please refer to the paper. Thank you.